Okay, so what I decided to do is rather than go into elliptic curves, which is what I'd originally planned after I finished this example of Pell's equation, I thought that instead I would actually keep the references in text and do something else. So rather than I didn't really think that I could cover enough. I thought I would basically leave you guys hanging with the two lectures that I had left if I tried to go into elliptic curves. So rather than do that, I'm just going to, if you're interested in heading in that direction, after I do a couple of examples tomorrow of lightly touching on stuff, then I will tell you, where you can go to have a look at that info. But I thought I would basically keep it in the text and try to give a good survey of some of the big stuff that comes up next in the text, especially with tying in continued fractions with Pell's equation. But before I get to that, I had outlined this Chakravala method yesterday for coming up with solutions to Pell's equation. So what I wanted to do um, was to do a fully worked example for that. So just reminding you, so this is Pell's equation for some positive integer d that's not a square. So we're looking for a pair xy in integers. So integer solutions to this. By this theorem, these are always guaranteed. The condition that x is not plus or minus 1 means that it's not the trivial solution. So non-trivial solutions to this are what we're looking for. And so this Chakravala method that I outlined yesterday is the following. The idea is that, so this is just explaining what it means to multiply triples in this way. Uh, if you don't like thinking of it, from the ground up, there's a form that these modified triples are going to take that you can just remember that form if you like, instead of doing it from the definition like this. So this corollary here that I've pushed down for a second is that there's actually infinitely many solutions in XY. So typically when you talk of these things, you'll hear a lot, what's the smallest integer solution, smallest positive integer solution to this that's non-trivial, right? Will be something that you hear here. And a lot of times the smallest non-trivial positive integer solution to this is really large. So we saw an example of that when when d is 61, for instance. The solutions are like the smallest positive integer solutions, x and y are both like really huge, like I don't know, like 12 digits or something. Okay, so anyway, for relatively small d, the smallest positive integer solution to this can be really big. Anyway, so here was the outline of the Chakravala method. So basically, what I do is the following. So and I can't remember if I wrote this. I'm gonna write this at the top of the next page before we begin doing the actual example. So the idea is that I start with an arbitrary triple, and by a triple ABK, what I mean is an equation a squared minus db squared is equal to k. So for some positive d that is not a square, so fixed positive d that's not a square, a triple relative to that d is a, b, and k satisfying this. Okay, so it's like Pell's equation, except the right-hand side is this k instead of 1, right? And the goal, of course, is to find a triple with k equals 1. Okay, and so the way that this process works is basically if I let E be the GCD of B and K, then if this GCD is not 1, basically I can, any prime divisor of the GCD, I can divide A and B by P and K by P squared to obtain a smaller K. You can keep doing that until B and K are relatively prime. Okay, and once B and K are relatively prime, the idea is you can multiply this triple abk by m1 and m squared minus d, where m is something that is some integer I haven't chosen yet. The idea is that when I do that, I get a triple that looks like this. So this is what I was saying. You can just remember this form. You don't have to go back to the definition of multiplying triples. You can just remember this this form. And so looking at this, I am going to divide. So I'm going to divide the equation by k squared, which leads to this equation, which means that I get a triple am plus bd over absolute value of k, a plus bm over absolute value of k, and m squared minus d over k. This is the triple that I get. But the thing is that it's not necessarily a true triple, because when I say triple, I mean these are all integers, right? So the only way that this works out, right, is if these numerators and these fractions are actually divisible by k. That is, if they are congruent to 0 mod k. Okay, and so what do we do here? The idea, this is the important part. So after I've done this process, I choose m to be a positive integer such that a plus bm is congruent to 0 mod k, and such that this absolute value of m squared minus d is as small as possible. So what does this do? If a plus bm is 0 mod k, it means that k divides a plus bm, so that this thing is an integer, right? Okay, so choosing m in this way guarantees that this thing is an integer. So then for this equation to give me a new triple, right, not only this thing has to be an integer, so I've chosen m such that this thing, a plus bm over absolute value k, is guaranteed to be an integer. But I need to know that these other two quantities are also guaranteed to be integers, and that's where this lemma comes in, which says that if you've chosen m such that a plus bm is congruent to 0 mod k, then the other two quantities are integers as well. Okay. So then this gives me a triple, right? So the lemma says that if I've chosen m such that a plus bm is 0 mod k, then I get a triple, which is defined by am plus bd over absolute value of k. In the first slot, a plus bm over absolute value of k in the second slot, and m squared minus d over k in the third slot. Okay, so notice absolute values here, but not one here. Okay, and if I've chosen m such that the absolute value of m squared minus d is as small as possible, and I continue to do this at each step, then eventually I terminate this process with a third slot that is equal to 1, i.e. a solution to Pell's equation. Now, I'm going to show you later how this is related to continued fractions. But for now, this is our method for coming up with solutions to Pell's equation. And this is the same method that Bhaskara used to find that wacky solution that I mentioned yesterday. Okay. All right. So, how do I actually go about doing this? Let's pick an example. So here's an example. Let D equal 19. I want to use the Chakravala method to find non-trivial integer solutions to x squared minus 19y squared equals 1. Okay. All right. So I can start with any triple I like. I'm going to start with 516. And the reason why I'm going to start with that is I'm going to just try to do computation. I'm going to start out with 5 for x. So 5 squared, that's 25. If I subtract 19 from that and multiply that by 1 squared, what's the result? The result is 6, right? That's 25 minus 19. So that's 6. That's not 1. Okay, but that was my attempt. Okay, and so I start with this failed attempt, right? So I plugged in 5 and 1 because I thought maybe it was close enough. It didn't work. So I get this failed attempt here, which gives me a triple 516. Okay. Now, again, didn't have to start that way. This is just what I decided to do. Okay. All right, so we have 516. Okay, so now I want to multiply by m1 and m squared minus 19. Where does that come from? Let's go back to my step. So my step here says I want to multiply this triple by m1 and m squared minus d. So m1 m squared minus 19 is what I want to multiply by. Again, you don't have to remember that. What you can remember instead is that the triple that I get when I do this process is, so this is the triple I get from multiplying, but after I've divided, the triple I get is am plus bd over absolute value of k, a plus bm over absolute value of k, and m squared minus d over k. So maybe I should say, so after dividing by k, I get the triple. So I'll write it out this time, but then I'm just going to write the final result after that. So I get the triple here. Oh, actually, I've already written it up here on the same piece of paper, so that's good. So I get this triple here, right? Okay, so there it is. So I am just going to write the final result. So this is am plus bd over absolute value of k. That is 5m, b is 1, d is 19, so this is 5m plus 19 over k is positive 6, so absolute value of k is 6. Next, a plus bm, a is 5, b is 1, so this is 5 plus m over 6. And lastly, I have m squared minus d over k, so that's m squared minus 19 over 6. Okay. Now, what is my next step? Well, let's go back to my Chakravala process method. This is the commandment to choose m to be a positive integer such that a plus bm is congruent to 0 mod k. So a plus bm is the numerator in that middle thing in the triple. So this is 5 plus m in this case. So we want to choose 5 plus m to be congruent to 0. We want to choose m in such a way that 5 plus m is congruent to 0 mod 6. Okay, and we want to choose m that satisfies that in such a way that m squared minus d is as small as possible, or rather the absolute value of that's as small as possible. So we need, this is by that lemma, we need 5 plus m is congruent to 0 mod 6. Okay. i.e. m is congruent to 1 mod 6. But since we need the absolute value of m squared minus 19 to be as small as possible, we need an m that's congruent to 1 mod 6, but also m squared minus 19 to be as small as possible. So m equals 1 is our choice. Okay. And so if we choose m to be equal to 1, note that all of these things are going to be integers, right? So this choice yields a triple. So choosing m equals 1 yields a triple. And the triple that you get from this is, just go back here, so 5 times 1 plus 19, that's 24 over 6, so that's 4. 5 plus 1 over 6 is 1. And 1 squared minus 19 is minus 18 over 6, that's minus 3. All right, so this is 4, 1, minus 3. Okay, this corresponds to the equation 4 squared minus 19 times 1 squared is equal to minus 3. Okay. So we repeat the process with our new triple. So we repeat our process for the triple 4, 1, minus 3. Okay. So repeating this process where we multiply by m1, m squared minus 19, and then divide by the absolute value of k in the first two slots and k in the last slot. What do I get? So I get the triple 4m plus 19 over absolute value of minus 3 is positive 3. In the next slot, I have 4 plus m over absolute value of k, which is 3. And in the last slot, I have m squared minus 19 over k, which is minus 3. Okay. So we need to choose m such that we go to the middle slot, it's the numerator, so we need 4 plus m to be congruent to 0 mod 3. Okay. So we need 4 plus m to be congruent to 0 mod 3, such that m squared minus 19 is as small as possible. Or rather, as I said, its absolute value is as small as possible. So m needs to be congruent to 2 mod 3, right? That's what this says. So we need an m congruent to 2 mod 3 such that m squared, or the absolute value of m squared minus 19 is as small as possible. So the smallest m for which that's true is 5. So m equals 5 is our choice. Okay, and this choice gives another triple. And if we choose m equals 5, I have 20 plus 19, that's 39 over 3, so that's 13. Next, I have 9 over 3, that's 3. And last, I have, so 25 minus 19 is 6 over minus 3, so that's minus 2. Okay. And we repeat the process, right? So repeating this process, or I could say this corresponds to the equation 13 squared minus 19 times 3 squared is equal to minus 2, right? So repeating the process, what triple do I get? I get 13m plus 57 over positive 2. That's the absolute value of minus 2. So 13m plus 57 is what I get in the first slot. In the second slot, I get 13 plus 3m over 2. And in the last slot, I get m squared minus 19 over minus 2. And if you're confused where that comes from, just remember really quickly, this is the formula for it. Oop, let me push this up. Right. So this is where we're getting those numbers. Okay. All right. So, so after I repeat this process, this is what I have here. Now, I want to turn this triple. I want to make sure that this triple is an integer triple. So what do I need to do? I look at the middle numerator, and I need I need m such that 13 plus 3m is congruent to 0 mod 2. And I need the absolute value of m squared minus 19 as small as possible. Okay. So 13 plus 3m is congruent to 0 mod 2. What does that mean? That means m is congruent to 1 mod 2. Right. So I need an odd m, right, for which m squared minus 19 is as small as possible. Again, m equals 5 is our choice. This leads to another triple. So the next triple that we get from this is if m is 5, so I have 5 times 13 plus 57 over 2. So that's 122 over 2, so that's 61. Okay. Then I have 13 plus 3m. If m is 5, that's 13 plus 15, so 28 over 2, that's 14. Okay. And then lastly, this is 6 over minus 2. So this is minus 3 again. Right? And you might be a little bit concerned because maybe you had hopes that these last slots, right, these K's would be kind of forever getting closer to 1 at each step, but you see that that's not the case, right? And so after you've worked through a couple of examples of these, you know, you might think that maybe there's some choice of D that makes this process never terminate, okay? But thankfully, Lagrange showed that this always terminates. You always end with a 1 here. So, you know, and you can look in the textbook to see why that is. I think that's outlined. It might be outlined in one of the projects. I'm not sure. But anyway, the point is that this process always terminates, so you don't have to worry about that. Even though, like, just looking at this, it might not be clear we're getting closer to an actual solution here. So this corresponds to the equation 61 squared minus 19 times 14 squared is minus 3, apparently. Right? Okay. So let's multiply to get our next triple. So our next triple is multiplying this by m1, m squared minus 19. My next triple is 61m plus 14 times 19 over 3. Next, this is 61 plus 14m over 3. And lastly, this is m squared minus 19 over minus 3. Okay. So I need 61 plus 14m to be 0 mod 3. Okay, so I need this to be 0 mod 3, i.e. I need m to be 1 mod 3. Okay. And m equals 4 is the one that gets this done, such that m squared minus 19 is as small as possible. ASAP, as small as possible. Okay. So if I let m be 4 here, I have 61 times 4 plus 14 times 19 over 3. If you compute what that is 170. And I have 61 plus 14 times 4 over 3. That is 39. And, oh, look what happens, right? M squared 16 minus 19, that's minus 3 over minus 3, that's 1. So this is my triple. It ends in 1, and I am done. Okay? So, this last triple corresponds to 170 squared minus 19 times 39 squared is equal to 1, which is exactly our solution, right? Thus, x equals 170, y equals 39 is our desired solution to x squared minus 19y squared equals 1. So Pell's equation of d equals 19. Okay. So you see, even a choice of d yields, you know, some integers here. These aren't like massively huge, but they're big enough that, you know, trying to do this by eyesight is, you know, just looking at it, right, and testing values is hard. So definitely need some, you know, some nice process that makes this, you know, a lot more manageable. Okay. So it turns out that this is intimately related to continued fractions. Okay. Okay, and so that segues into what I wanted to talk about next, which is the topic of chapter 17, which is continued fractions. Okay. So what is an example of a continued fraction? Well, probably the simplest example of continued fraction is one that just involves ones everywhere. So 1 plus 1 over 1 plus 1 over 1 plus 1. Need more room here, right? Over 1 plus 1 over 1. And I'm just going to continue that. A lot of times you'll have these dots will be slanted to indicate that it is continuing downward in this fashion. So here's an example of a continued fraction. Okay, meaning that whatever this number is, it is continuing on in this fashion. This is an example of continued fraction that is what we'll call periodic. So I won't define that right now. Although you can look at it and see maybe what I'm going to mean by that. But this is a simple example of one that's periodic. It's also an infinite continued fraction in the sense that this process just goes on forever. So this continued fraction form continues indefinitely. There's no last term here, right? It just keeps going like this. Okay, and so you might have seen this particular continued fraction before, and so if you were to try to, figure out what this continued fraction was, you might try to estimate it, right? So if you wanted to approximate this, you might look at like this truncation, right, where you have stopped it at this point. And so this is 2. And you might say, well, this thing is like approximately 2. But of course, you stopped it so early in its continued fraction form that you know this isn't going to be that great of an approximation. So maybe you do something like this. You stop it here, right? So if you stop it here, this is 1 plus 1 over 2. So that's 1 and 1/2, that's 1.5. Okay, and so maybe you say that's a better approximation, but maybe not the best still. So you continue going. And maybe this is your next thing. Now these are all 1, so this isn't too bad. So then this is 1 plus 1 over 1 plus 1 over 1 plus 1. So this denominator is 1 plus 1/2. So that's 3/2, right? And so this is 1 over 3/2. So this is 2/3. This is 1 plus 2/3, right? So this is 1.6 repeating. Okay. And this is a better approximation, of course, but so all these are approximations. This is getting to be a better approximation of this thing, but it's still an approximation. Now for this fraction, it has a simple enough form that we can actually figure out what this thing is, right? This has a simple enough expression that we actually know what this thing is going to be exactly. We don't need to approximate, but this is giving you an example of how you would approximate this. I'm going to talk about in a second how starting with a number you can come up with a continued fraction that approximates it, and where this comes from, or why this is something that's nice. But anyway, and you might already have seen from this approximation that I'm getting here what this thing is. But to see what's really going on here, we're lucky in this case. We can do something special, right? If I say that whatever this thing is, I want to call that whole quantity x, well, due to the nature of this, right, I have 1 plus 1 over stuff. And if I circle this stuff, right, if I circle this stuff, well, what do you notice about this, right? If I circled that and I put my hand over this, coming and looking at this expression, you say, well, that's the same as the expression we started with, right? And it is. So whatever this x is, it's the same as 1 plus 1 over itself, right? So really, this is 1 plus 1 over x. Right? And so, multiplying by x here, whatever x is, when you square it, that's the same thing as adding 1 to it. Right? Okay, so okay, but then what is this? So, I mean, I get two roots here. I'm just going to look at one of them. Right, it's this thing. Right. So this is the golden ratio, right? This is phi. Okay. Of course, this is you might object and say this is either phi or phi inverse or something. But anyway, the point being that this is just an alternate form of the golden ratio, and so is expressed as this simple continued fraction. Now, we're going to talk about continued fractions in the sense that ones that actually terminate, so they have a last term. But we're also going to talk about ones that would go on forever or would infinitely repeat in some way, so would be periodic, for instance, in this example. So, what do I want to say about continued fractions? So, the spiel at the beginning of chapter 17 is pretty good, so I'm going to present it in its entirety before actually writing some stuff out here, because I'm actually interested in our applications of this to Pell's equation. So anyway, the motivation here is, and maybe I'll going to have to actually, I think this is fine. Yeah, you can see that. Okay. So, Christian Huygens faced a challenge in 1680. The Dutch astronomer was designing a mechanical planetarium for the Royal Academy of Science in France. He calculated that in a 365-day year, the Earth goes through an angle of, you see this angle, this annoying little fraction of a degree here that is extra, right? So it's 359 degrees and then some extra bit. And so writing that out in base 60, the problem is that you have this very annoying fraction here rather than something nice. So you have this annoying fraction here. You're building a planetarium, so you got, all the planets in the solar system here. Saturn goes slower, and Saturn's particular annoying fraction is this one. And therefore, if you want the relative motions to be accurate, you would have to, if you're designing this mechanically, so you have gears, you would have to have the ratio of the gear teeth to be the following, right? So you're taking the numerator of the one you get from the Earth and dividing it by the numerator of what you got for Saturn. So the ratio would be this thing, which is it's approximately like 29 and some change, so 29.42545. That's what you would need in order to make these relative motions accurate. But the problem is that these numbers you're dealing with here are huge, right? And so if you're designing this mechanically and you want to know how to build your gear, like how many teeth, right? So if you have a bunch of like triangular teeth on your gears, to have the ratio in this amount, you would need to actually build gears, right? Looking at this thing, having that number of teeth, right? And the gear for Saturn would have this number of teeth, and that's how you'd have to build it. But of course, these are ridiculously huge numbers, right? So you do not want to build a gear with that many teeth. That would be crazy. So what you want to do is to come up with a fraction that approximates the fraction that you started with that's annoying, that has much smaller numbers, right? And sometimes it's not a matter of being able to reduce these. Sometimes you can't reduce them, right? This could be in lowest terms. I'm not sure if this one's in lowest terms, but it could even be in lowest terms, so you can't really reduce them. So this is not something you can solve in that way. So you need to come up with a fraction that is simpler to work with. And so it turns out that the fraction you could use instead, if you wanted to, is 206 over 7, because 206 over 7 is approximately the same thing. Okay, now, where did he come up with 206 over 7 for approximating this fraction? It was from continued fraction. So to see that, basically, he looked at this decimal, right, and used this decimal to express this gigantic thing as continued fraction in this way. So expressing it as continued fraction, this would be 29 plus 1 over some stuff. I'll talk about where this came from, but let me show the rest. So depending on how many digits of this thing that you are willing to write out or know, using the digits in this decimal expansion, you can come up with this continued fraction expansion for this particular rational number. So this is what it looks like. Okay, and there's no implication here that these things are repeating or anything. This just continues on in some fashion. Okay, so that's what my continued fraction looks like. And what you can do to come up with this approximation, 206 over 7, is you can just stop at a nice point. So for instance, you could just stop here and compute whatever that number is. Okay, and so that's exactly what he did, stopping before the 5. We'll talk about later why the 5 clues you in that you should stop. Okay, but stopping right before the 5, you compute 29 plus 1 over 2 plus 1 over 2 plus 1 over 1, and what you get is that it's actually 206 over 7. Okay, you'll quickly notice that these things can be very annoying to compute with, and we'll go over the process that will save you a lot of hassle there. Okay, and so this is where this approximation came from. So one, might not be, well, it depends on what your definition of practical is, but the idea is one practical use of this is if you have a rational number that, even though it is a rational number, it's very annoying to deal with, maybe because the actual integers involved in the numerator and denominator are huge, and you want to approximate that with a rational number that's more manageable. So continued fractions is a way to do that. Okay, so here's another example. Say you got the number pi, right? So number pi is 3.1415926535897. Okay, so let's see. 265, we'll stop there. Okay. All right, so that's what pi is. If I want to approximate pi by a rational number, there's a couple of options, of course. So, and of course, this depends on how close I want my approximation to be. So, what I could do is say 314,159 over, say, 100,000, right? That's one way of doing it. So, pi is approximately this. If I'm okay with it agreeing to like 6 decimal places or something, okay, that's fine. But a better approximation is given by 355 over 113, which is 3.14159.292, and so on. Okay. Okay. Now, you could say, well, I know a lot of digits of pi, so I could have just literally copied like 100 digits of pi and then put them over, 10 to the 100 if I wanted to. I could definitely do that and have a better approximation than I got here. So what we mean by better is that the number of digits, right, the size of the integers p and q here, if this is a fraction, p over q, are smaller. So that's what we mean. So it is true that if x is a real number, then there exist integers p and q such that the absolute value of x minus the rational number p over q is less than 1 over q squared. Okay. Okay. I don't think I'll prove that later. I may mention this as part of a theorem later, depending on how far I go into continued fractions. But this is a fact. And so, for instance, pi minus 22 over 7 was 22 over 7, I believe, was the ancient Egyptian approximation for pi. Also might have been the Greek. Was it the Greek approximation as well? Maybe that was the case. I can't remember. So this is approximately like 0.00126, which is less than 1 over 7 squared. And pi minus 355 over 113 is approximately like 0.0000027, which is less than 1 over 113 squared. But pi minus the example that we did here, so 314,159 over 100,000. So this is approximately 0.0000265, which is bigger than 1 over 100,000 squared. Okay. So we would consider this not as good of an approximation as these two in that sense. Okay. All right. So I know that might seem a little bit counterintuitive, but that's the idea. Okay. All right, but the big question as I said, is how do if I gave you some truncated continued fraction, then knowing absolutely nothing from anything that we've done in this course, obviously you could crank out what that thing is just by brute force, you know, adding fractions. But how do you go in the opposite direction? How do you generate like an approximate continued fraction for some real number? Okay, so question, how do I come up with an approximation in the first place? In this way, I'm not talking about the dumb way of doing it like we tried by just writing the digits over, you know, some powers of 10. So how do I come up with an approximation using this? So for example, let's consider pi, right? So pi is, again, 3.14159266. Yeah, we'll just stop at 265. Okay. So I look at this thing and I extract off the integer bit. So pi minus 3 is just 0.1415965. And so what I do here is I look at this bit of the decimal that's left over, and I want to try to come up with, you know, the first part of the continued fraction for this thing. Okay, and so the idea is this is less than 1, so we invert. Okay, and when you invert, of course, you know, you could do this by hand. It would be extremely annoying, so you will use, you know, computational tools like calculator or whatever your favorite computational tool of choice is. So if you invert this, you get 7.0625133 and so on, okay, which you can write as 7 plus that extra bit. Okay. How does this help you? Okay. Well, you could say, okay, pi is approximately 3 plus 1 over the integer part of this is 7. So this is like 3 plus 1 over 7 is an approximation, but that's 22/7. So that's one thing you could do. The other thing you could do, so maybe you're happy with that. Maybe that's a fine approximation. But the other thing is to take this bit and try to continue this continued fraction for this extra decimal bit. And so you have 0.0625133. If I invert that, because that's less than 1, so if I invert this, again using favorite calculator of choice, this is 15.99659 and so on, which I can write as 15 plus 0.99659 and so on. Okay, so pi is equal to 3 plus 1 over 7 plus 1 over 15.99659 and so on, right? This is what pi is equal to. Thus, pi is approximately 3 plus 1 over 7 plus 1 over just the integer part of this is 15. So this is 3 plus 1 over 7 plus 1 over 15, which is 333 over 106. Okay. All right. Which you can compute is a pretty good approximation for pi. Okay, but let's go one step further here by wanting to find continued fraction bit for this. So it turns out that 1 over 0.99659 so on is 1 point, it's very close to 1, it's 1.0034, right? And so using this, what I get is the following. So pi is 3 plus 1 over 7 plus 1 over 15 plus 1 over 1.0034 and so on. Okay. Okay. And so, if I want to approximate, I can just cut off this bit. So this is 3 plus 1 over 7 plus 1 over 15 plus 1 over 1. The integer part is 1, so this is 1 over 1 here. And so what is this? If I go through the hassle of actually computing this, this is 355 over 113. Okay. Now we could continue, and if we continued, we would get 1 over 0.0034 and so on. This is like 292.63 and so on. So the fact that this is big, relatively speaking, the fact that this is big compared to the previous integer parts that have shown up is a good indicator that we could stop before and get a very good approximation. Okay, there's a reason why that's true that, like I said, I'll mention later. But this is why before I said there's a reason why stopping at 5 I knew would be a pretty good idea. So this is what a continued fraction looks like, and this is how to generate it from, like, say the decimal expansion. Okay, this is how you could go about coming up with these continued fraction approximations. Okay, so then notice that you might say, if I write out more than just like 3 or 4 terms these continued fraction, it is going to take up like all of my paper. So I need to come up with a better notation for writing these continued fractions. So what is the idea behind writing out a continued fraction? So notation. So my notation for continued fractions is if I write out bracket A0, A1, A2, and so on, well, I'll just end there. So it repeats, okay, indefinitely. This is defined to be A0 plus 1 over A sub 1 plus 1 over A sub 2 plus 1 over A sub 3 plus so on. Okay. So this is what I mean by this bracket notation for continued fractions. Okay. All right, and this will This will save me a lot of time and effort. Okay, so how do I compute these quickly? So what is a good way of computing a continued fraction quickly? Because after you do a couple of examples of these, even if you only wrote out like, 5 or 6 terms here, you will see that it is very, very annoying to compute. And if the thing you're dealing with is an approximation, then necessarily, like, if you're trying to do it by brute force, if you did the approximation for the first, 5 terms, and you'd already finished that computation and you saw, oh, this isn't as close of an approximation as I wanted, I want a closer one, and then you try to do it for 6 or 7 terms, you'd have to redo the whole computation, right? That's how this works. That's how a continued fraction would work like this. You'd have to redo the whole computation. It would be insanely annoying if that were to come up. So surely there's got to be a method that allows you to not have to deal with that kind of nonsense, and there is. So here is the method. So I'm going to write it out. In the notation, it's not really going to make a whole lot of sense, so I will immediately do an example that shows what this notation means. Here's the following proposition that explains how to compute these things quickly. So let A0, A1, A2, and so on be positive real numbers. Okay, this is just to define these things, to initialize them. Let P sub minus 2 be 0, and Q sub minus 2 be 1, and let P sub minus 1 be 1, and Q sub minus 1 be 0. Okay. For K greater than or equal to 0, define P sub K to be A sub K times P sub K minus 1 plus P sub K minus 2, and define Q sub K to be A sub K times Q sub K minus 1 plus Q sub K minus 2. Okay, it's a lot of indices to keep track of. Then P sub n over Q sub n is the same, this fraction is the same as the continued fraction A0 to AN. So this is our notation for continued fraction here. Okay. And this is true for each n. Any ratio P sub k over Q sub k is called the kth convergent of the continued fraction in question. So I'm not going to really use that terminology, but that's what it's called. Okay. So let's do this for the example that we did before with pi. So 3 plus, so this is 3 plus 1 over 7 plus 1 over 15 plus 1 over 1, right? So say that we did this, okay. All right, and rather than computing it this way, I wanted to say, well, this is in continued fraction notation, this is, oh, it's not that, it's 3, 7, 15, 1. Okay. All right, so what is the idea? How does this work? Okay, the way that this works, the way to read these indices is to set up a table. Okay, so here's the table we set up. So maybe I should include this before I actually get into the example. So we form the table Okay, so we form the table, which is the following. So so these two entries are blank. Here is A naught, A1, A2, A3, A sub 4, and so on. Okay, these I fill out the initialization quantities for P and Q. So this is the statement of P sub minus 2 is 0, P sub minus 1 is 1. Here's Q sub minus 2 is 1, Q sub minus 1 is 0. So what goes here in these entries is P naught, P1, P2, P3, and P sub 4, and same thing with the Q's. You'll see how we compute them here in a second. All right, and then if I want my fraction in question, I just take the ratio P sub k over Q sub k. At any step is going to give me varying approximations, right? So that's the idea. So when I'm doing this for the continued fraction 3, 7, 15, 1, I form the table that looks like this. So this is 3, 7, 15, 1. And then here goes 0, 1, 1, 0. So now I need to compute P naught. Now looking at these equations here defining my indices, so P naught would be A naught times P sub minus 1, which is 1, plus P sub 0 minus 2, so P minus 2, which is 0. So it would be 3 times 1 plus 0. So it is, rather than trying to remember the indices, the easiest way to do this is looking at this table. You take this entry here, you multiply it by the previous entry in the first row. So if we are computing the entry in this row, then we're going to be using this row's the previous entries in this row to do it. So it's 3 times 1 plus 0. So 3 times 1 plus 0 is 3. If I want the entry in this row, it would be 3 times 0 plus 1, so 1. I do the same thing for each of these. Of course, I'm using these numbers immediately previous. So this would be 7 times 3 plus 1. So that's 22. 7 times 1 plus 0, that's 7. What is this column saying? It's saying that here's an approximation for pi, 3 over 1. Well, okay. Then here's another one, 22 over 7. Right? Next, I have 15 times 22 plus 3. So that's 330 plus 3, so that's 333. Okay. Next, I have 15 times 7 plus 1. That's 105 plus 1, so that's 106, which gives me that other approximation, 333 over 106. And then lastly, 1 times 333 plus 22 is 355, and 1 times 106 plus 7 is 113, which gives me that last so this is the full fraction here. So this is 355 over 113. Okay. But you see how this table includes all of those previous approximations if I wanted to truncate, right, and stop at any of these points. And what is really nice about this is, let's say that situation comes up that I mentioned before where I realize, oh, this isn't actually a good enough approximation. I want a different one. Including another step, I can easily do that. I don't have to recompute the whole fraction. I can actually just put that next entry in this table and I can just keep computing. Okay. All right. So that's the benefit of doing it this way. So this is just a practical matter of how you would by hand compute these continued fractions. Okay. So what does this have to do with Pell's equation? So now to bring it back to Pell's equation. All right, right, so we have x squared minus dy squared is equal to 1. Right, where d is some positive integer, it's not a square. We can rewrite this. Okay, we can rewrite this as x squared over y squared minus d is equal to 1 over y squared. All right, so I divide both sides of the equation by y squared. That's what I get. So note that x over y is very close to the square root of d if y is large. Why? Well, x squared over y squared, or x over y all squared, is very close to d if y is large, and so x over y is very close to square root of d if y is large. Okay. And so what we do is we look at continued fractions for square root of d. So idea, look at continued fraction for square root of d. So here's an example. Let's do this for Pell's equation that we solved earlier today using the Chakravala method. So if d is equal to 19, then I'm looking at continued fraction for square root of 19, which you can find in that exact same method we use for pi. This continued fraction is 4, 2, 1, 3, 1, 2, 8. 2, 1, 3. I keep writing it next to each other. 1, 3, 8. So those are all commas in between here. 2, 1, 3, 1, 2, 8. Sorry, that's not a 1, 3, 8. That's a 1, 2, 8. So 2, 1, 3, 1, 2, 8. And this continues on. And I am implying that actually the 2, 1, 3, 1, 2, 8 keeps repeating after that point. So I would write that as 4, 2, 1, 3, 1, 2, 8. And I would put a bar over the last 6 terms, denoting that they repeat forever. This is an example of a periodic continued fraction. Okay, which is similar to our discussion of periodic decimal expansions. All right. So that's what we get. Okay. So I could write out that table to compute the various increments of this continued fraction for a bunch of steps if I wanted to. But what I think I'll do instead is show you the table so that I don't have to waste time writing all that. So let me get it up close. Okay, there we go. So here's the numbers p sub k and q sub k for this continued fraction. All right, so these numbers can be computed in the exact same way that I just computed that table for the continued fraction. And so what we do is, looking at these numbers, here is an 8. And 8 is relatively large compared to the numbers that came before it. And so I get the idea that it's a good place to stop to get a good approximation for this continued fraction, the step before. But what do you note about the numbers in the step before? I get 170 and 39. And as we saw earlier today, that was the exact solution that I got using the Chakravala method. 170 squared minus 19 times 39 squared is equal to 1. If we go to the next 8 in the table, the next 8 happens here off the table. Okay, so we get the idea that it would be a really good idea to stop, okay, before, and that is this last column, And if I look at those numbers, it's not immediately clear the relationship, but it turns out that for those numbers we have this. So 57,799 squared minus 19 times 13,260 squared is equal to 1. And as is noted here, this is not a coincidence. Okay. So this is the result of the following theorem, which gives us a way of solving this Pell's equation using continued fractions. Said, oh, I'm out of focus. It can't find writing. Maybe I should start writing so that it knows what's going on. Okay, there we go. So, theorem. So this is the thing that ties in Pell's equation and continued fraction. So let d be a positive integer, not a square. The continued fraction for square root of d has the form, this is always true. Okay, so I won't prove this immediately, but it has the form a naught and then a periodic part. So a sub 1, a sub 2, and so on, all the way out to a sub n minus 1, a sub n. This is the periodic part. Okay, this is always guaranteed. Okay, where a sub n is equal to 2 times a naught. Notice our a naught for our previous example was 4, and the last number showing up in this periodic part was 8. Okay, so this is always true for square root of d, where d is a positive integer, it's not a square. Okay, we have a sub k is less than or equal to a naught for all k between 1 and n minus 1. So let m be greater than or equal to 1, and let x be given by, well, both x and y. So x is p sub mn minus 1, and y is q sub n minus 1. The p and q this notation comes from that previous proposition to compute these continued fractions. Then x squared minus dy squared is equal to plus or minus 1. Okay. Now, if it's equal to plus 1, we're happy because that solves Pell's equation. If it's equal to minus 1, it turns out we're happy because we can get a solution to Pell's equation out of this. Okay. So then how do I solve Pell's equation using this? So solving x squared. Nope. So solving x squared minus dy squared equals 1. How do I do it? So first step is to compute a naught. A naught was 4 when we were looking at square root of 19. What's the relationship between 4 and square root of 19? It's the least nearest integer, right? So this is the floor function of square root of d. All right, so a naught is the floor function of square root of d. That's the first thing I do. Step 2 is compute the continued fraction. Which is bracket a naught, a1, a2, and so on for d, or for square root of d. Okay, and I stop when a sub n is equal to 2 times a naught. So I keep going until I get an entry that's twice my starting entry, right? My starting term. So 3, let x sub 1 equal p sub n minus 1 and y sub 1 equal q sub n minus 1. For if x sub 1 squared minus d times y sub 1 squared is equal to 1, then I'm done. Right? I have found x and y that solve it. I can just say x is equal to x sub 1, y is equal to y sub 1 solves Pell's equation. And lastly, if I'm in the other case, right, if x sub 1 squared minus d times y sub 1 squared is equal to minus 1, because that's what the theorem guarantees, it's either plus or minus 1, then I compute whatever x plus y times square root of d is, whatever these x and y are, such that they are equal to x sub 1 plus y sub 1 times square root of d squared. Okay. So write out x sub 1 plus y sub 1 times square root of d, square that, combine terms, put them in this form, you get an x and a y, and that solves Pell's equation. Then this x and y solve Pell's equation. I'll put a little stone here because this is the end of the process. So you have ended this process with a solution to Pell's equation. Okay. All right. So this gives you another way of solving Pell's equation using continued fractions. All right. So there will be a question involving Pell's equation on your exam, which I'll post a little bit later today. If I didn't mention it previously, I am going to post. I'm going to post your. I'm going to post your final exam later today, and then I'm going to have office hours tomorrow at the usual time, so 2 to 3:30. And you can ask me whatever questions from any of the course material. You can ask me questions about the final exam. Like I said, I will give hints and I will help, but I won't be maximally helpful. I'll just kind of point you in the right direction. So anyway, that's the plan. So tomorrow I'm going to finish up with a survey of some of the stuff that fills out the remainder of the book basically, and I'll give you all some info on where, depending on what aspects of the course you're interested in, where you could go from there, with textbook recommendations and all that. So anyway, I'll see you tomorrow, both for lecture and office hours if you want, and be looking for I'll post an announcement when I post the your final exam later. But anyway, so be looking for that.